So good afternoon. We're going to do a lesson on logarithmic functions. So this is going to be lesson 4 of this unit. This comes from chapter 6, section 4. So again, we've talked about an exponential function, and we mentioned it is a one-to-one function. So it has to have an inverse. So recall how to graph the function y equals 2 to the x. So remember, we had these 3 key points. 0, we put 0 in. Let's see here. Let me get this going here. So we pick x to be 0, x to be 1, x to be -1. And remember, the points that must exist on the function y equals 2 to the x's. If you put 0 in, we got 1. If you put 1 in, that gave us 2. And -1, remember, that meant to take the reciprocal. 2 to the -1 actually would be 1/2. So if we graph those 3 points, we'd have 0, 1, 1, 2, and -1, 1/2. That'd be the 3 points. Also remember that the x-axis was a horizontal asymptote. So in graphing our function, we kind of see that the x-axis is the boundary line. And this graph kind of will then start to shoot up like so and make this kind of graph here. So if I want to graph the inverse, let's see. What we're going to pick up on is the x's and y's have to switch places. So the y's become the x's and the x's become the y's. So they switch rows. So 0, 1 becomes then this 1, 0. This 1, 2 becomes this 2, 1. And this -1, 1/2 becomes then this 1/2, -1. So if I graph those 3 order pairs, 1, 0, 2, 1, 1/2, -1. And also what happens is the asymptote switches from horizontal. It's now actually becomes a vertical asymptote. So this boundary line is now going to be the y-axis. All that stuff switches over. So instead of having, the horizontal asymptote being y equals 0, it's now going to be x equals 0. It's now going to be a vertical asymptote. So all the rows of x's and y's switch. So when I graph my function, we should now see that it now is going to be approaching the y-axis, and it's going to be kind of veering off in this direction here. So one thing to also pick up on is the graph and its inverse should be symmetric to the line y equals x. So I didn't do a great job of sketching these out, but you should be able to see that there is some similarities there, that they are kind of being mirrored across the line y equals x. So we do have the graph of the inverse. Now the catch is, what we want to do moving forward is we actually want to find the inverse. So if we want to find the inverse function for the exponential function, this f of x equals 2x. Remember, to find the inverse, we have to switch the x and y values, and we have to solve for y. So if I have this y equals 2 to the x, if we switch the rows of x and y, we have now this x equals 2 to the y. So we have this x equals 2 to the y, but we have to solve for y. But how do we get y by itself? We really have not solved one of these. So what happens is there's not really a strategy to solve this function. So what we do is we create a new function, and it's called a logarithmic function. So what happens is if you have x equals 2 to the y, then the inverse is we write this, the exponent comes down as one side of the equation, y equals, and then we write this as the log of x base 2. So notice that the exponent becomes one side of the equation. The 2, which was the base, becomes the base of the logarithm. And then the x becomes what we're taking up the log of. So it becomes our domain. So over here, notice how, y would be the domain and x would be the range, but we don't want that. We want this to be x to be the domain and y the range. That's our normal way of doing that. So that starts to make a little bit better sense in the form of this notation. So again, the 2 is called the base and the y becomes the exponent. That's the 2 important things to pick up on here as we move forward. So if I have a logarithmic function with a base a, if we have this notation x equals a to the y, then I can write the inverse as y equals, or I can write the equation also as y equals the log of x base a. So in these forms, this is referred to as the exponential form. And this form here is referred to as the logarithmic form. So these 2 forms mean the same thing. They're just in different forms, if you will. Something else to pick up on is the domain for a logarithm is x is greater than 0. Notice how if you look back up the graph, notice how the red graph was our logarithmic graph. This represented this y equals log of x, if you will. And this is actually base 2. Notice that the graph does have a vertical boundary, which meant you could not go past the y-axis. So that means all your x values are to the right of the y-axis. In other words, x's are greater than 0 here. So we pick up on that our domain is x is greater than 0 because x equals 0 was the vertical asymptote, but our graph is actually to the right of the vertical asymptote, so x is greater than 0. That's going to be our domain. So that's something we need to pick up on about a logarithmic function is its domain is this. So some things we're going to be doing in our homework, changing an exponential equation into its equivalent form of a logarithmic equation. So if we have 1.2 raised to the 3rd power equals m, I can write this as a logarithm. Now, the way I do it is I focus on the exponent first. That becomes one side of the equation. So this becomes 3 is equal to then, and then I use my log form. So the log of, the base is the 1.2, which means the m would have to be what we're taking the log of. So 3 equals the log of m base 1.2 would be the way of reading that. So if I have e to the b equals 7, if I want to put that in logarithmic form, again, the exponent becomes one side of the equation, so the b comes over here. And then I'm going to take the log of something, but the base is the e, so that goes here. So what I'm actually taking the log of is the 7. So b equals the log of 7 base c would be how I would read that. So if I have a to the 4th equals 64, the logarithmic form, again, the exponent is the 4, equals the log of, well, the base is a, so we're taking the log of 64. So so 4 equals the log of 64 base a would be the logarithmic form of the equation. If I want to change a logarithmic equation into an equivalent form of an exponential equation, so again, we have logarithmic equations given. If we want to rewrite that in an exponential form, so again, what I do is I focus on the base, which is the x. And the exponent would actually be the 10, and that would equal then the 4. So notice that the x and the 10 are what going to go together. So that they're going to come together as one side of the equation, and the 4 becomes the other side of the equation. So it's kind of unpacking the logarithm, if you will. So if I have the log of b base c equals 3, again, the base is the e, the exponent is the 3, that becomes one side of the equation, and that's going to equal then this b. So again, the e and the 3 go together to create one side of the equation, and that creates the exponential form of the logarithmic. So if I have log of 5 base 3 is equal to n, the exponential form is going to be 3 to the n is equal to then this 5. That's going to be the exponential form. So the next thing we have to do is evaluate a logarithmic expression. One way of doing this is just think in the form of an exponential. So if I have the log of 8 base 2, that has to equal something. We have to evaluate that. So remember, evaluate it though, the 2 is the base. What we're looking for is actually the exponent. and that has to equal then this 8. That's where our thinking takes us. So if I can answer that question, then we've evaluated the logarithmic expression. So 2 to the what power is 8? Well, that would be a 3. So that would be the answer to this problem, is a 3. So if I have the log of 164 base 4, again, what I'm looking for is actually the exponent. So my thinking is 4 to the what power equals 1/64. So essentially, I'm kind of writing this in exponential form in my thinking. So this is a mental step, if you will. I don't actually have to show that on paper, but that's what my thinking is. So 4 to the what power is 1/64. First off, just think of 4 to the what power is 64. Well, that would be 4 times 4 times 4. That would be 64. But to make it a fraction, the exponent would have to be negative. So 4 to the negative third would be our answer to that problem. That would be the exponent that makes 4 turn into a 1/64. So next thing we have to do is find the domain of a logarithmic function. So remember, the domain of the parent function is x is greater than 0. So now if we look at this function here, k of x equals the log of x minus 4 base 2. Notice now we have what we call a transformation, this minus 4. Remember, if that minus 4 is inside, so what happens is our graph actually shifts to the right 4, which means our domain should shift to the right 4. But as far as the strategy goes, what we can also do is set the x minus 4. We can set that polynomial to be greater than 0 because it has to be greater than 0. And remember how we solved inequalities back in the last section. If we find the 0, in other words, if I set x minus 4 equal to 0, that would give me x equals 4 is a 0. So using a number line concept, we have 4 is on our number line. We want to test the intervals to the left and right of the 4. So if I pick a number left of 4, say 0, 0 minus 4, well, that would be a negative 4. Well, that means if you go left of 4, that's negative, which means if you go right of 4, you should probably get a positive value. So a number that's right of 4 would be, say, 5. 5 minus 4 would be 1. That's a positive value. So notice that my domain where it's positive would be, notice how we cannot include 0, we cannot include 4. We have to be to the right of 4. So my domain, if I'm using set builder notation, would be the set of x's such that x is greater than 4. If I'm using interval notation, it would be open. We do not include the 4. 4 to infinity would be the domain written in interval notation. So if I have g of x equals the log of 1 plus x over 1 minus x base 4, if I want to find the domain of this, what I do is I set the 1 plus x over the 1 minus x. That domain of that has to give me something that's greater than 0 to evaluate this. So what we pick up on here there's two things. The 0 is what makes the numerator 0. So 1 plus x is got to be equal to 0. So in other words, x would equal negative 1. That would be the 0. But remember, we also have to identify the domain restriction. The domain restriction is the denominator. So if I set the denominator to 0, 1 minus x is equal to 0, we'd have negative x equals negative 1. X would equal then this 1. That would be my domain restriction. So if I graph these two pieces on the number line, this will help us identify the next part of this problem. So the catch is negative 1 would have to go to the left and positive would have to go to the right. We have to identify the larger and the smaller value there. And remember, greater than 0 means we're looking for a positive value here. We're looking where the interval is positive. So if I pick a number left of negative 1, say negative 2, that would be over here somewhere. If I test that, that would be a negative 2 plus 1 on the top. And negative 2, oops, try to do that again. I'm replacing x with negative 2. So I didn't do that right on either one of them. Let me try that again. So I'm replacing x with the -2. So the numerator becomes 1 plus -2. And the denominator becomes 1 take away -2. So the numerator becomes then this -1. And the denominator becomes what's 1 plus 2, which would be a 3. We know that a negative divided by a positive would be a negative. So left to -1, we would end up getting this negative value over here on this side. A number that's between -1 and 1 would be 0. So if I want to test 0, we could put that in for x. So 1 plus 0 would be the top, and 1 minus 0 would be on the bottom. Well, that would be 1 over 1, which is a positive answer. So between -1 and 1, we would have a positive value. So if we go right of 1, a number that's right of 1 would be maybe a 2, if we test 2 there. So we tested a -2 there. So let's test a 2 over here. So that'd be 1 plus 2 on the top, and we'd have 1 minus 2 on the bottom. So it's going to be 3 over a -1, which again, that answer would be a negative. So over here would be a negative. So what we're looking for is where it's positive. It looks like it's positive between -1 and 1. And again, we cannot include either boundary, so it's got to be open-ended. So if I'm using set builder notation, it's going to be the set of x's such that I'm between a -1 and a 1. If I'm using interval notation, it's going to be -1 to 1 using interval notation. So as we move forward, properties of logarithms, as we said, that the domain is going to be x is greater than 0. The range is going to be the set of real numbers. And the x-intercept is going to be 1, 0. It's not going to have a y-intercept, and it's going to have this vertical asymptote. So as we try to graph this function, notice how if we knew how to graph y equals 2 to the x, the inverse is going to be these rows switched. So if I change this into a logarithmic function, we'll do that here in a second, but we have this here. So we have, remember, 0, 1, 1, 2, and -1, 1/2, where the points for the parent function of y equals 2 to the x. Now remember, we have to change this to find its inverse, the rows of x and y have to switch. So this becomes then x equals 2 to the y. But to solve for y, what we can do is put this in logarithmic form, which would be y equals the log of x base 2. So if I want to graph the parent function of this function, the logarithmic function, the rows of the x and y's have to switch. So this becomes a 1, 0, a 1, 2, and a -1, 1/2. So that's how, again, if we evaluate this, if I have the log of 1 base 2, 2 to the y power gives me 1. 2 to the y power gives me 1. Well, that would indeed be 0. If I want to do this, let's see here. I got that one backwards there. Sorry about that. I didn't switch the rows on these last two, did I? Okay, so let's try to switch the rows of those. So 0, 1 became 1, 0. 1, 2 becomes 2, 1. And -1, 1/2 becomes 1/2, -1. We have to switch the rows there. So if I want to evaluate the log of 2 base 2, well, 2 to the y power is 2. 2 to the y power is 2. Notice how that would be a 1. And if I have the log of 1/2 base 2, you know, 2 to the y power is 1/2. That would indeed be a -1. So those order pairs do play out there. So graphing a logarithmic function, I have to kind of go back to the exponential function to start with, and then I can kind of start picking up on that, because really I'm used to the exponential more so than the logarithmic at this point, until I get a little bit better at that. So let's see where we have here: 1, 0, 2, 1, and 1/2 -1. That's where those points would be. Now the catch is, though, we're trying to graph this function. So if I want to graph this function, notice how that negative is on the inside. Since that negative is on the inside, that should affect the y value. I'm sorry, that should affect the x values. Okay. So if I want to make the table for the log of -x base 2, since the negative is on the inside, that means that the rows of my x's should all change. So this 1, 0 becomes a -1, 0. This 2, 1 becomes a -2, 1. And this -1/2 -1 becomes a -1/2 -1. So the y values don't change, only the x values do. So what happens is the parent function, all the order pairs flip across the y-axis. So -1, 0, -2, 1, and -1/2 -1. Those become my new order pairs. These guys now are moved over. So notice how this becomes then the graph of my new function. It kind of takes on this look. So notice how, again, the x-axis is the, the y-axis is the vertical asymptote. So notice how x = 0 is the boundary line. That's the vertical asymptote that's also imperative in graphing this. So that's basically what we need, is the vertical asymptote. We have to pay attention to it, and then if we can identify some order pairs, we can kind of graph the function. So if we have, again, f of x equals the negative log of x minus 1 base 2, what we pick up on is our parent function is y equals the log of x base 2. So notice that in graphing this, what we know actually is the 0, the 1, and the -1 are now my y values. And we have this 1, 0, this 2, 1, and this 1/2 -1 become our x values. Remember how the rows of x and y switch. So we have those order pairs are in my parent function. And I got those by using the inverse of the exponential function. So we knew 0, 1, 1, 2, -1, 1/2. And now those rows all switch. So we now graph 1, 0. Oops, I'm sorry. We're going to make the transformations here. So we have to observe the x minus 1 and the negative on the outside. So the negative on the outside is going to change the rows of my y values. They're all going to get reflected. So 0 doesn't change, but the 1 turns into a -1, and the -1 turns into a +1. On the inside, the -1, remember, the inside is always backwards. So if that's a -1, that means I have to add 1 to all of my x values. So 1 plus 1 becomes then this 2. 2 plus 1 becomes 3. And 1/2 plus 1 would be 1.5 or 1.5. So when I graph this, we have now 2, 0, 3, -1, and we have 1.5, 1. So we have that kind of going on. So what I got to pick up on is what's going on here. Well, notice that also, if there's a shift in the x's, the asymptote has to also shift over 1 as well. So the asymptote that was at 0 now moves over to x = 1. So now we kind of see this graph here. And notice that this negative on the outside, that's a that's a vertical reflection, which means this graph should now be reflected upward instead of downward. So my new graph should now be going in this direction. It kind of gets reflected and going off in that direction there. That would be the graph of the logarithmic function based on the transformations. So again, notice how again, when we do a function, we have the equation. If we can make a table, we can then create the graph from that. So the natural logarithm. So again, we talked about this e's what's called a natural number. If the base of a logarithm is base c, what we're going to pick up on is there's going to be what's called a natural logarithm. So if we have y equals log of x base c, notice how e is the base of the logarithm. What we do is we use this notation y equals ln of x. So we write the natural logarithm in the shortcut format, which is this right here. So you'll see this as the most common format. So remember, these are equivalents. So keep in mind, the exponential form is going to be e, x equals e to the y. Or, we can also flip it around where e to y equals x. So that's going to be the exponential form. So again, if I have the log of x base e equals y, the exponential form is going to be e to the y equals x. Remember, e is the base, y is the exponent, and then the x comes and forms the other side of the equation. So either one of these is going to be used as the exponential form. And remember, e also represents this number 2.718228, that approximation. So if I want to graph this function y equals e to the x, if you recall, this exponential function, we had 0 gave me 1. So remember, e to 0 would be 1. If I put 1 in, e to the 1 would be e, which we would say is about 2.7 if I was going to estimate that. So that's the approximation. And e to the negative 1 was 1 over e. So when x is negative 1, that was 1 over 2.7, which we round to about 1/3 as an estimation there. So that was our approximation. So in graphing this, I can graph the inverse by switching the rows of the x and y. So I have this 1, 0, I would have then e1, and I would have like this 1 over e negative 1. In other words, 2.7 here and 1/3 here would be the values. So notice how, again, to graph the inverse, the rows of x and y switch rows. So 1, 0 would be a key point. Instead of E1, we do 2.71. So it's about here. And instead of doing 1 over E negative 1, we use 1/3 negative 1 as an estimation. Notice how, again, the x-axis is our vertical asymptote there. So we'd have this vertical asymptote going down through here. So if I want to graph the logarithmic function, it's going to take on the look of, it doesn't look much different than that base 2 one. Very similar. So its characteristics are very much the same, just shifted over just a little bit because of e's a little bit bigger. What we also have is what's called a common logarithm. A common logarithm, the base of the logarithm is 10. So again, in our books, we call that the common logarithm. So if I have y equals log of x base 10, this also could be written as y equals the log of x without the base. So if you see the log of x, it's understood that that base is a 10. It's not shown. It's understood to be there. So just like square root symbol, that with that radical symbol, if I give you the square root symbol, it's understood to be a 2 there. Instead, we just write this as the square root. That radicand and the index number is not shown in the square root symbol. So just like in a logarithm, if the logarithm is a base 10, then the notation you'll see is log, without the base. So if I have 10 to the y equals x, I can also write this as, y equals the log of x. Because notice how, again, if I want to write this in logarithmic form, that's going to be the log, it's going to be y equals, because the exponent goes on one side, and then that would be the log of x base 10, if I was changing that back. Because remember, the exponent becomes one side of the equation, and the 10's the base. We don't show it, though when it is a base 10, we leave it off. That's understood there. So if I have the log, I'm looking for is the exponent, and it's understood to be a base of 10. A 1. So we've learned that from our properties of exponents that if 0 is an exponent, the answer is a 1. So if I have the log of 1/10, that equals something. What that really means is, again, there's this base 10 here that's understood. So it's 10 to the what power is 1/10. And remember, what turns a 10 into 1/10 is a negative exponent. So we understood that that's a negative 1 as an answer. So if I have the log of the square root of 10 equals something. So again, our base is a 10. 10 to the what power is the square root of 10. Remember, what exponent is the same thing as the square root symbol, and that would be the 1/2 exponent. So that is the exponent of 1/2, because remember that represents the square root of 10, or the square root symbol. So these are interchangeable. So 10 to the 1/2 is the same thing as the square root of 10. So we had that as a rational exponent that we talked about earlier. So the next thing we're going to get into is solving logarithmic equations. One thing to note, the base of a logarithm is going to be a positive number. So if I have the log of b base a is always going to be a positive value. So keep that in mind as we move forward. So if I want to solve a logarithmic equation, what we want to do, if possible, is just write the logarithmic back into write the logarithm back into its exponential form. The other thing is, as we learned in the previous section, if we can make the bases the same, then all we have to do is set the exponents equal to each other and solve. So if I want to figure out, the log of x base 3 is equal to 2, if I want to figure out what x is, basically what I'm doing is saying, 3 to the second power is equal to x. So if I look at this problem, I can solve it by just simply evaluating the left side, 9. So x equals 9 would be the solution to that problem. So the log of 9 base 3 would be 2. So that would be our missing value, would be the 9. So if I look at this next example, the log of 3x plus 4 base 2 is equal to 5. If I want to solve this logarithmic equation, what I can do is put this in exponential form. That's going to be 2 to the 5th is equal to 3x plus 4. So again, on this one, I would probably rewrite this the other way around. I would rather have the variable on the left side. So I'm going to rewrite this as 3x plus 4. And 2 to the 5th is the same thing as, let's see, we know that 2 to the 3rd is 8. 2 to the 4th is 32. 2 to the 5th must be 64. If I did that correctly. 2 times 2 times 2 is 8 times 2, 16. That should just be 32, isn't it? So take that back there. Yeah, that's just 32. 5 2s is 32. Okay. So the next thing would be to subtract 4 from both sides. And we would have then 3x equals 28. Divide both sides by 3, and you'd end up with 28 over 3. And that fraction doesn't reduce, so we just keep that as 28/3. So that would be our solution to that one. So if I have x log of 16 base x equals 2, this would be x squared equals 16. So if we solve this for x, we'd have to take the square root of both sides. That's the shortcut. X equals plus or minus 4. But remember, the base cannot be negative, so the answer ends up being just x equals 4 based on the restriction there. So if I have the natural log of e to the negative 2x equals 8, remember, this is the same thing as the log of e to the negative 2x base e is equal to 8. So if I rewrite that back out like that, we recognize that this does have a logarithmic form with a base. So if I put that in exponential form, we're going to have e to the 8 equals this negative 2x. I'm sorry. Try that again. E to the 8 is going to equal e to the negative 2x, because this is what we're taking the log of. So since the bases are the same, we can just set these equal to each other. I'm going to go ahead and put the variable on the left side. So negative 2x equals 8. If I divide each side by negative 2, we would have x equals this negative 4. That would be the solution to that problem. So notice how I can put that in exponential form. The bases are the same, so all I have to set the exponents equal to each other to solve for x. So if I have the log of 64 base 4 equals x, again, I can write this in exponential form as 4 to the x equals 64. Again, 4 to the power 64, I think we did this earlier. We learned that that is this x equals 3. 4 times 4, 16. 16 times 4 would be 64. So that would be the answer to that problem. So if I look at this next example, I have the log of 36 base 6 equals 5x plus 3. One way of doing this problem is using exponential form. So this would be 6 to the power of 5x plus 3 equals 36. I'll put that in exponential form. Notice 6 and 36 don't have the same basis, but 36 can be expressed as a base of 6. So I can leave this as 6 to the 5x plus 3. I'm allowed to change 36 to 6 to the power of 2, because that's the same thing as 36. Now, since I do have the same basis, this is now solvable. Set the exponents equal to each other. 5x plus 3 is equal to 2. So if I subtract 2 on both sides, subtract 3 on both sides, I'm going to get 5x equals negative 1. Divide both sides by 5, I would get x equals this negative 1/5. So that would be the answer to this equation, is x equals negative 1/5. So let's look at solving an exponential equation using a logarithm. So some equations, like I said, can be solved better looking at the logarithmic form. So if we have e to the x equals 10, what we can do, let's see here, if we could change this into logarithmic form. So this is going to be, notice how the exponent becomes one side of the equation. So this becomes x equals, and then what we can do is take the log of, and our base is e, we have the log of 10 base c. So whereas this becomes x equals the natural log of 10. And so that would be the answer. If we need to change that to a decimal, then we can use the calculator to do that. So that concludes our lesson on working with logarithmic functions.